G'day. I pulled this little electronic kit out of my collection of bits and pieces that I've had floating around for many years. I think I would have put this together back in the early 1980s, believe it or not, and I've still got it floating around in my junk pile. Basically it's a little electronic dice. Used to have this push button here attached on the end, and when you push the button the lights flash and then stay on a dice number of obviously between 1 and 6. But as you can see, it's bits and pieces falling off. The battery connection has been cut off and used elsewhere probably. You can see that it's a very basic etched old PCB. It was a kit from an early Australian electronics magazine, probably Electronics Australia or Electronics Today International. I've done a bit of a search on Google. There is absolutely no information about this whatsoever. So what I might do is clean it up a bit, see if it works, and maybe just reverse engineer it and just trace out the drawing, see how it works, and yeah, play around with it. And at the same time I might be able to give you an idea on how some of these CMOS 4000 series chips work. We've got some quad NOR gate, we've got a Johnson counter, and what was this one? I think it's triple input NOR gates again. Pretty simple circuit, as you can see. So let's get it cleaned up and see if it still works. Okay, I've cleaned it up quite nicely using the old dishwasher method, and actually cleaned it up surprisingly well. It's the first time I've tried that particular method. I wouldn't advise that if you've got electromechanical devices like switches and so forth. Obviously I didn't have my switch attached at this stage, so there's nothing really that a bit of hot water is not going to hurt on a solid state board like this. So now I'm going to go ahead and just clean up some of these solder joints. Obviously some of them are pretty shoddy. I guess I was just a beginner solderer back in the early 1980s. Some of these are pretty atrocious looking solder joints. So we'll go ahead and do some cleaning up of the solder. Okay, I've actually gone ahead and removed most of the old solder off all of those joins and resoldered them because most of them were looking a bit dry after nearly 40 odd years. As we know, this board is dated at now. So now I'm just going to connect up the switch. I've salvaged the old battery connection wires. So let's see if we can just tin those and then add the switch. And somewhere around here I've got a snap-on 9-volt battery lead as well, so we can connect that at the same time. Okay, so we're all ready to test it now. We've resoldered every joint on the board, and I've had a quite close look at them, and they're all looking pretty good. About the only thing that's not original, I guess, is the switch was soldered directly to the board with a couple of PCB pins originally, but I've decided just to attach them to this little bit of cable. So we'll go ahead and connect up a battery and see what happens. It's probably a bit bright here. Let's dim the lighting. So as I hold on the button, all the lights come on, albeit a little bit dull. When I release the button, there is a pattern there. In that case it was 5, and after a short period of time they turn off. Press the button again, there's a 4, and it turns off. Press the button again, 4, it turns off. 3, 2, 6, 6, 1, 3, 5, 5, 6, 3, 6, 1, 5, and so on. All right, so let's have a little look. I've taken the time to do a little drawing of the circuit. Let's just zoom in on that for a bit. And let's explain exactly how this works. Well, near enough to exact anyway. There's some bits and pieces that I don't quite fully understand. Now, firstly, we've got a 4001 CMOS NOR gate there. So the first thing you should do when you're looking at circuits like this is to download a data sheet. and in this case it's the Motorola data sheet for a whole series there. You can see them all listed of different NOR gates and NAND gates. Okay, the one we're interested in particular is the 4001B, which is described as a quad 2-input NOR gate. Quad being there's 4 of them, and obviously 2 inputs per gate. And this diagram gives you the pinouts. On the next page, a diagram of the DIP package, the dual inline package, showing all the pinouts, as well as obviously the 0 volts and supply voltage. And the rest of the data sheet will detail all the different characteristics and more detail into how the gates are actually internally organized. Okay, so this document actually also accounts for the other chip on here, another chip which is the 4025, and in this case it's also a NOR gate. Where is it? There it is there, but it's the triple input, 3 inputs, so it's a triple 3-input NOR gate. The other chip on this board is also in the 4000 series of CMOS logic gates, and that is a 4017, and in that case it is it's got a 5-stage Johnson counter, or a decade counter, and in this data sheet we have a nice little functional diagram of how that operates, or how it's arranged I should say, as well as the pinouts. And some more detail of the actual circuitry inside the chip, which consists of a whole bunch of AND gates, buffers, NOT gates, there's a NOR gate, and flip-flops, which are basically a couple of NOR gates or NAND gates in an arrangement. And the buffered outputs through these other gates. So essentially what happens here, you apply a clock pulse to the clock pulse input, and for each clock pulse the output will increment by 1. So this will be on for the first pulse, then this one will be on, that'll be off, they'll all be off, it'll just be 1 at a time, and it counts up to 10. Thus, that's why it's called a decade counter. But obviously for a dice, we really only need to count to 6. And so if we look at the way that what we do there is we when it gets to output 6, we loop around to the master reset, and then once it does a reset, it will count up, increment up each time. So back to our little drawing here. This is the actual circuit arrangement. We've got, in this case I've used the IEC symbols for NOR gates. Basically that's the standard in Australia, but you might more commonly see them as the traditional symbols used in most textbooks and so forth, which is this symbol here. Okay, so essentially you need to understand how NOR gates work. And let's have a look here. I'll look in my book of the reference book as the Forrest Mims Engineer's Notebook is a particularly handy piece of literature. And let's have a look here. What do we got? It's got a nice little page here which shows some what's called truth tables for how the NOR gate works. Okay, so basically for the OR gate, you have any input on and it'll give an output or a high or a logic 1. So 0, 0 or low, low will be a low output. The NOR gate simply inverts that output, and so it's the opposite. So the only time the output is on basically is when both or all the inputs are low or 0. So NOR gates can be up, there's some NOR gates that are 8 inputs, I think. If we look at the ones down the bottom there, got 8 input NAND gates and NOR gates. But it's the same principle. It doesn't matter how many inputs, they all have to be low to enable the output. That's a very quick introduction to how a NOR gate works. Now, that first chip on the board is arranged and uses up all 4 of those NOR gates. This first part of the circuit here is what generates our clock pulse, pulse generator, and it's set up, I believe, not entirely sure, but it is a astable multi-vibrator. So it's when you turn on the switch, the push button here, there's a pull-up resistor there. It starts free running with the pulse coming through on the clock pulse input to the Johnson counter. It feeds back here through, and that's how it's generating the pulse. I won't go into too much detail about how that works because I don't fully understand it myself actually, but I do know that this resistor and capacitor are what determines the time and the frequency of the pulse train that comes through. Now, the other gate, NOR gate, is down the bottom here, is the one that determines how long the display lasts for. You'll notice that after I release the push button, the value of the dice is displayed for some seconds and then it turns off. And that timing is determined by this resistor and capacitor componentry down here. And once again, that's activated through this switch via this diode. Okay. So obviously we need to be able to randomize the counts. The whole idea of a dice is to produce a random number. And the way they've done this is by having a pulse that's quick enough so that the randomizing is generated by how long really you press the push button for. And you're not going to be able to trick the dice or anything because the time that you press the push button is more or less a random time compared to the frequency of the pulse train that goes through. So it's a very, very fast frequency. I'm not sure what it is. I haven't really worked that out, but it is, by doing that, you sort of generated a pseudo-random bit of logic there. Right, so we've got our pulse train coming through and our clock. So you're starting from here, there's output 0 right down through to output 9. And so the pulse train goes from 0 down through to 5, and then at 6 it goes into a master reset. And then so it goes just through those first 0 to 5, which is 1 to 6 more or less. All right, and then we have some clever arrangement of the NAND, the NOR gates here, and there are our LEDs. So I've numbered them. I'm not sure if hopefully you can see that all right on the drawing. Down the bottom here, that's the arrangement of how I've numbered the LEDs. 1, 2, 3, 4, 5, 6, and 7. So let's go for by count. So as you can see here, the first count is not actually connected. So even though there's a 1 output on there, it's not actually used, and all these others are 0 or low. So if you remember a NOR gate, if all your outputs are low, then the output of those NOR gates will be true, or 1. Okay, so in this case they're all high because there's no inputs on each of these. They're all zeros. So the way this circuit works is obviously your flow is coming. This allows current through the LEDs, but if this is 1, because these are also 1, there'll be no flow through these 3 lines here. But this one here, you'll notice, doesn't actually go through a gate, and it goes directly into output 1 of the Johnson counter. Now that we've already said is low, because each of these are low except for that first one, which is not connected. So that allows flow through these 2 LED diodes, which is 7 and 1. 7 and 1 gives us a display of 2 for our dice count. So a little diagram down here of to keep track of these is our dice number and then our count number. So for a count of 0, which is 0, corresponds to the output 0 here, we're displaying 2. So that's the state of the outputs, 0 to 5. Okay. For our next count, it increments down to output 0. That one turns off, and as the others remain off as well. So in this case, we've now got a 1 on here, and all the others are still 0. But because that's a 1, this output goes to 0. Right. Now, once again, once we've released the finger off the button, that comes high, and then obviously, so we're going to get a flow through LED 4 because this is a 0. But in this case, we won't get a flow through these ones because this output has gone to high. So in this case, the only LED lit is number 4, which is the center one, and that gives an indication of 1. All right, and then we move on to the next count, 2. So now these are all low or 0. 3, 4, and 5 are 0. It's only output 2 that is high. So in this case, we have a high there, so we've got a low here. These remain both high because there's no inputs. And so in this case, because this one's now turned off and going low, we're back to having a flow to illuminate both these ones, and now we're illuminating LED 4 as well. So it's these 3 LEDs are lit. If you look down on the letter arrangement here, 1, 4, and 7. So this count gives us an indication of 3. Okay. So then we move on to the next count with the next clock pulse, and that is output 4. So when that one comes on, and this time we're getting a high on both these 2 NOR gates, so they'll both be now low outputs. And output 1 will also be low. So in this case, all of these LEDs will come on because we've got low, low, and a low. So 3, 5, 1, 7. I think I missed output 3, sorry. All right, well, it doesn't matter. We'll stick with count 4, output 4. And this center LED is also on. So that is count 4, an indication of 5. So that's those 5 LEDs are on. So just going back to output 3, the previous count step. In this case, it's only driving this NOR gate here to go low. The others remain off. And 3 and 5, yeah, and also 1 and 7 will stay on because that remains low. So that is 1 and 7, 3 and 5. So that gives you your dice indication of 4. Okay, so then we'll explain count 4, and then the last one goes to 5, output 5. In this case, we're driving both of these NOR gates to give a 0 output there and there. This one remains high, but this one again remains low as well, so we're getting a flow through 6, 2, 3, 5, 1 and 7, which is 1 and 7, 3 and 5, 2 and 6, which is those 6, which gives a dice indication of 6. And then the next count, it goes straight into a master reset, so it skips the back to the beginning. You did notice, I presume, that the dice numbers are out of order here, even though the last 4 are 3, 4, 5, and 6. The first 2 are asked about, but that really doesn't matter because the whole idea is we're generating just a random pattern of LEDs, and it really doesn't matter what order that the dice numbers are displayed, because we're generating a pseudo random response via the time that we've triggered, the time our finger remains on the push button, and it sets up a fast enough train of pulses that when you release your finger from the button, it'll stop at some random count. Okay. So there you go. That is a brief explanation of how you can use CMOS 4000 series logic gates to create a little novelty dice display. Okay, well, thanks for joining me. We'll catch you on the next episode. Cheerio.